Right now, astronomers think the observable universe contains around 2 trillion galaxies. That number is so huge it almost dissolves into noise. If you tried to name one galaxy every second, you would still be counting thousands of years from now. Yet under a dark sky, you see only a few thousand stars, and maybe a faint blur of Andromeda. Between those familiar pinpoints and that absurd tally lies a puzzle. How can we possibly know there are that many galaxies? And what if that number is not just incomplete, but deeply wrong? Stay with this journey, and if you enjoy exploring the cosmos, remember to like this video and subscribe so you do not miss what comes next. You and I are used to numbers that connect to daily life. 10 minutes, $50, 100 messages waiting on your phone. 2 trillion galaxies lives far outside that comfort zone. It is like trying to imagine every grain of sand on every beach on Earth, and then being told that number is still too small. The human brain did not evolve to keep track of the universe. It evolved to decide whether that rustle in the bushes means dinner or danger. Counting galaxies, then, is not like counting chairs in a room or trees along a road. You cannot just take a picture and tally them one by one. Even if you could see every galaxy clearly, you would be trying to count tiny smudges scattered across a sphere so large that light itself needs billions of years to cross it. The task is impossible in any direct, simple sense. Astronomers had to invent a different way to think about the problem. A better picture is to imagine standing on the shore of a vast ocean with only a small net in your hands. You dip the net into the water, pull it out, and count the fish inside. You do this over and over at different spots and different depths, and from that limited collection, you try to guess how many fish live in the whole sea. That is what astronomers are doing with galaxies. Our telescopes are the nets. The patches of sky we stare at are the places where we sample. From those small, carefully studied regions, we try to infer the full population spread across the entire sky. Of course, that ocean story hides all kinds of complications. Some fish are big and bright and easy to catch. Others are tiny or shy or live so deep that your net barely ever touches them. In the sky, the bright showpiece galaxies are like the big, obvious fish. They leap out in telescope images and make posters for science museums. The faint, diffuse galaxies and the smallest dwarfs with only a scattering of stars are like the deep-sea creatures. They are there in enormous numbers, but our instruments keep missing them. Even the sky we see with our eyes misleads us. When you step outside on a clear night and look up, it feels as though you are seeing the universe. In reality, you are tasting only the thinnest foam on an immense wave. Most of the stars you notice live in a tiny neighbourhood of the Milky Way. You do not see the full disk of our galaxy, only a gentle river of light stretching overhead. You do not see the enormous halo of dark matter that holds everything together. And you certainly do not see the countless galaxies beyond, whose light is too faint to register on your retinas. For most of human history, that was where the story ended. Philosophers and early astronomers could wonder whether those faint patches in the sky were clouds of gas or entire island universes, but they had no way to test the idea. Only in the last century did we confirm that the Milky Way is not the whole universe, but one galaxy among many. Only in the last few decades did we even attempt to put a serious number on how many others are out there. When those first estimates arrived, they were already staggering. Based on earlier observations, many astronomers repeated a rough range of 100 to 200 billion galaxies in the observable universe. That alone was enough to make us feel like residents of a crowded cosmic metropolis. Then fresh analysis of deep observations and computer simulations pushed the estimate upward by a factor of 10. Overnight, the story shifted from hundreds of billions to around 2 trillion. Same universe, same sky, completely different sense of scale. Here is the unsettling part. No one has actually seen 2 trillion galaxies. No camera has ever captured that many in one grand census. The famous number is an inference, a best guess built by combining what we can see with what we think we understand about how galaxies form and grow. It leans on models, assumptions, and populations of galaxies that are too faint or too far for us to detect directly. In other words, our proud galaxy count rests on a huge collection of things we have never truly laid eyes on. In the chapters ahead, we are going to unpack that process step by step. We will ask what even counts as a galaxy when the line between clusters, dwarfs, clouds, and streams grows fuzzy. We will follow the bold observers who pointed the Hubble Space Telescope at patches of sky that looked empty and discovered thousands of hidden systems. We will explore how time, distance, and the expansion of space itself bend our view of the cosmic population. And we will see why the phrase observable universe is a giant asterisk attached to every galaxy number you ever hear. By the time we are done, 2 trillion will no longer sound like a random trivia fact. It will feel like a hard-won, still evolving answer to a deep question about reality. You will see how much evidence it rests on, how much it ignores, and how much room there is for revision as new observatories come online. Most of all, you will understand that counting galaxies is not really about the tally itself. It is about learning how to ask the universe a careful question and then listening closely to the reply. Before we can count galaxies, we need to answer a deceptively simple question. What exactly is a galaxy? It sounds obvious at first. You imagine a majestic spiral like the Milky Way, packed with stars, dust lanes, and glowing nebulae. But as soon as astronomers started finding stranger and stranger systems, that clear picture began to blur. Is a galaxy defined by how big it is, how many stars it has, whether it has dark matter, or how it formed? Different answers lead to different galaxy counts, and our famous 2 trillion number quietly depends on where we draw that line. Let us start with the Milky Way as our reference. Our home galaxy is a barred spiral system roughly 100,000 light-years across. It likely holds on the order of 100 billion to a few hundred billion stars, along with giant clouds of gas and dust where new stars are still forming. All of this orbits within an invisible halo of dark matter that outweighs the visible stars and gas. Everything inside this structure is gravitationally bound, meaning the galaxy's own gravity keeps it together over billions of years, despite the motion of individual stars. That picture gives us a first draft definition. A galaxy is a large, gravitationally bound system of stars, gas, dust, and dark matter. It lives inside a dark matter halo, it can form new stars, and it evolves over cosmic time through collisions and mergers. Now we can compare that draft to other systems in the universe and see where it breaks. At the enormous end of the scale live giant elliptical galaxies like IC 1101. These monsters can be several times larger than the Milky Way, with hundreds of billions or even trillions of stars, often sitting at the centres of rich galaxy clusters. On the other end are dwarf galaxies, some of which are hardly more than star clusters with ambitions. Take Segway 2, one of the most extreme known dwarfs. It has only a few hundred to a few thousand stars, spread across a region that is still big enough to require a dark matter halo to hold everything together. If you looked only at the starlight, Segway 2 would seem pathetically small next to the Milky Way. Yet astronomers still class it as a galaxy because its dynamics betray a hidden reservoir of unseen mass. Between these extremes, we traditionally sort galaxies into 3 broad types. Spirals, like the Milky Way and Andromeda, have disks of stars, winding arms, and often a central bar. Ellipticals look more like smooth, featureless balls or stretched rugby shapes with little ongoing star formation. Irregular galaxies break the mold entirely. They have messy shapes, intense star-forming regions, and often show scars of recent gravitational encounters. At first, this neat classification scheme suggested a clear taxonomy. You could imagine lining up galaxies in a chart and assigning them labels the way biologists classify species. The universe, of course, refuses to stay inside neat boxes. As telescopes improved astronomers discovered systems that blurred the lines between galaxies and star clusters. Globular clusters are one example. These are dense, spherical collections of old stars, often containing hundreds of thousands or even millions of them, orbiting in the halos of galaxies like the Milky Way. They are compact, gravitationally bound, and long-lived. Yet they lack the extended dark matter halos and complex internal structures that galaxies have, so we usually place them on the cluster side of the border. Then came ultra-diffuse galaxies. These are objects as large as the Milky Way, but with 100 times fewer stars, spread out into ghostly, low-surface brightness disks or blobs. In a telescope image, they can look like faint smudges that almost vanish into the background sky. Some ultra-diffuse galaxies seem to be held together by massive dark matter halos, similar to normal galaxies of their size. Others appear to have very little dark matter at all, challenging our theories about how galaxies form and what keeps them stable. There are also tidal dwarf galaxies, which form not from pristine gas collapsing in a dark matter halo, but from debris torn out during violent collisions between larger galaxies. When two big galaxies interact, tidal forces stretch and warp their disks, flinging out long streams of gas and stars. In some cases, pieces of these streams collapse under their own gravity, lighting up as small, independent systems. Do we count these as galaxies in the same way we count traditional dwarfs? If a system has stars and gas, but little or no dark matter, does it belong in the same census as objects rooted in massive halos? Even more confusing are stellar streams. These are long ribbon-like trails of stars that wrap around galaxies like the Milky Way. They are the shreds of small galaxies or clusters that got too close and were gradually torn apart by tidal forces. At what point in that slow destruction does a dwarf galaxy stop being a galaxy and become a stream? For millions of years it might be part intact core, part trailing debris. A strict definition would need to pin down exactly when the transformation occurs, yet in practice, nature does not give us a clean switch. All these messy examples led astronomers to search for a more physical definition. One popular idea is to define a galaxy as a stellar system whose dynamics require significant dark matter. A globular cluster can be explained by the gravity of its visible stars alone. A dwarf galaxy like Segway 2 cannot. Its stars are moving too fast to be held together by their own mass, which implies a large, invisible halo. Under this rule, anything that needs dark matter to make sense qualifies as a galaxy, while anything that does not falls into the cluster category. Even that approach has problems. Measuring dark matter content is difficult, especially for faint, distant objects. You need precise velocities for many stars or gas clumps, and even then the uncertainties can be large. Interactions, mergers, and tidal stripping can complicate the picture further. Some systems may have lost much of their dark matter through past encounters, muddying the link between present-day dynamics and their original halos. A definition that depends on detailed measurements will always leave many borderline cases unresolved. This fuzziness is not just a philosophical headache, it flows straight into our galaxy counts. Deep surveys of the sky pick up a zoo of diffuse blobs, compact knots, streams, and clumps. Automated algorithms try to decide which detections are galaxies, which are clusters, and which are artifacts or overlapping stars. The choices made in those algorithms and the thresholds used in the catalogues directly affect how many objects end up classified as galaxies. Change the definition, and the count changes. So when you hear that there are 2 trillion galaxies in the observable universe, remember that the word galaxy hides a complicated story. It can refer to vast, structured cities of stars like the Milky Way, to dim dwarfs containing more dark matter than light, to oversized cotton candy ghosts barely distinguishable from noise, and sometimes to debris born from cosmic collisions. Before we even begin to map the universe, we have to decide who gets to live on that map. In the next part, we will see how a single, bold observation with the Hubble Space Telescope turned a patch of seemingly empty sky into a crowded city of these strange, diverse objects. In the early 1990s, a group of astronomers proposed something that sounded almost irresponsible. Take the Hubble Space Telescope, one of the most expensive scientific instruments ever built, and point it at a piece of sky that looked empty. No bright stars, no famous galaxies, nothing that would make a nice astronomy poster. Then leave it there, staring, for many days. To people who thought in terms of telescope schedules and budgets, this sounded like locking a luxury camera in a dark closet and hoping for a miracle. To understand why this was such a gamble, you need to remember where Hubble came from. Launched in 1990, it was meant to be the sharpest eye ever turned to the cosmos. Instead, engineers quickly discovered a flaw in its main mirror. The images were blurred, like a badly focused pair of glasses. It took a risky repair mission in 1993 to fix the optics and restore the telescope to the clarity that had been promised. After that, demand for Hubble time exploded. Every astronomer wanted a piece of that sharp vision for their own favourite target. Hubble orbits above the atmosphere, so its view is not smeared by the constant shimmer that blurs ground-based telescopes. That makes it ideal for detailed studies of planets, star-forming regions, and already known galaxies. Using it to stare at a blank patch instead of some famous object seemed wasteful to many. There were complaints that the proposal would hog observing time with no guarantee of a payoff. If the patch really was empty, they would end up with the most expensive picture of nothing ever taken. The team behind the idea had a different intuition. They suspected that the empty look of that patch was an illusion caused by the limits of ground-based telescopes and the sensitivity of the human eye. If you could stack many long exposures with Hubble's sharp optics, they argued, the apparent void might resolve into a deep background of faint galaxies. Instead of capturing a handful of bright objects, they wanted to drill a narrow pencil beam through the universe and see what was hiding far beyond our usual reach. The chosen patch lay in the constellation Ursa Major, away from the crowded band of the Milky Way and from bright foreground stars that might wash out faint light. On the sky, it was tiny. People sometimes compare it to the size of a grain of sand held at arm's length. That is not poetic exaggeration. The Hubble Deep Field covered an area of sky so small that you could easily block it with the tip of a ballpoint pen. If you walked outside tonight and looked up, you would never know exactly where it was. Over 10 days near the end of 1995, Hubble returned to that spot again and again, accumulating many hours of exposure in different colours of light. Each individual snapshot was still noisy and faint, full of random fluctuations, but when the data were combined, something remarkable emerged. The blank darkness resolved into a crowded city of nearly 3,000 galaxies, each a tiny smudge or spiral, frozen at different distances and times in the past. There were blue, irregular galaxies, redder, older-looking systems, distorted shapes that hinted at collisions, and objects whose light had left them billions of years before Earth even existed. For the astronomers who had argued that this would work, the Hubble Deep Field was a vindication. It proved that what looks like nothing at all can, with enough patience and sensitivity, turn into a cosmic forest of structure. It also gave them something more than a beautiful picture. Because the field was chosen at random and was so small, it could be used as a statistical sample. Count the galaxies in that tiny cone through space, correct for the volume that cone represents, and you can start to estimate how many galaxies might fill the entire sky. The excitement was so great that the experiment did not stop there. A few years later, the team performed a similar trick in the southern sky, producing the Hubble Deep Field South. Then, in the early 2000s, they pushed even harder with the Hubble Ultra Deep Field. This time, the telescope stared for hundreds of hours at a patch in the constellation Fornax. The resulting image went deeper than any optical picture of the sky before it, revealing nearly 10,000 galaxies in an even smaller area. In the ultra-deep field, some galaxies appear as tiny red dots, so faint that only their stretched, reddened light reaches us. These are among the most distant known galaxies, seen as they were when the universe was only a small fraction of its current age. Looking at that image is like holding a time machine in your hands. Every colour and shape corresponds not just to a different location in space, but to a different chapter in cosmic history. Young, chaotic galaxies crowd the distant background. More settled spirals and ellipticals dominate the closer layers. By combining multiple deep fields and correcting for the shape of the observable universe, astronomers arrived at those early estimates of hundreds of billions of galaxies. They took the number of galaxies in each deep field, adjusted for the fact that the density of galaxies changes with cosmic time, and scaled up to cover the full sky. The result was already staggering. Yet even as those numbers made their way into textbooks and documentaries, careful astronomers added a warning. These images were still limited by what Hubble could see. One major limit is surface brightness. A compact galaxy with many stars crammed into a small region shines brightly and stands out against the background. A galaxy with the same total number of stars spread over a much larger area looks dimmer and more diffuse. At some point, it simply blends into the noise, like a whisper at a loud concert. Hubble's deep fields were exquisitely sensitive, but they were still blind to galaxies whose light was too spread out, or whose stars were too few. Another limit is wavelength. Hubble is most sensitive to visible and ultraviolet light. As the universe expands, light from very distant galaxies is stretched, or redshifted, into the infrared. That means some of the earliest galaxies never show up in Hubble's cameras at all. You could stare at their part of the sky for 1,000,000 years with that telescope and still miss them, because you are listening on the wrong channel. At best, you see the brighter, more compact pieces of that ancient population. On top of all this, there is cosmic variance, the fancy name for the fact that the universe is clumpy on large scales. Some directions happen to pass through slightly more or fewer galaxies than the average. If you are unlucky and pick a patch that is a little underdense or overdense, your galaxy count will be biased. By using several fields in different directions, astronomers try to average out that randomness. Still, they knew that any estimate based on a few small windows onto the sky would remain uncertain. The Hubble Deep Field and its successors were a gamble that paid off beyond expectations. They turned apparent nothingness into a detailed cross-section of the universe, revealed galaxies at times and distances we had never probed before, and gave us our first serious handle on how many galaxies might inhabit the observable cosmos. Yet those breathtaking images were also just the beginning. In the next part, we will see how astronomers took this deep field data, combined it with models and simulations, and pushed the galaxy count from hundreds of billions up to around 2 trillion. For a while, the story seems settled. The deep Hubble images had given astronomers a way to sample the cosmos, and the early estimates all circled around the same ballpark, something like 100 to 200 billion galaxies in the observable universe. It was a neat, memorable number, big enough to inspire awe and simple enough to repeat in documentaries and textbooks. Then a team led by Christopher Consolis went back to the very same data and asked a sharper question. What if we are missing most of the galaxies that are actually there? Their approach was to treat the deep fields not as final answers, but as clues. Every galaxy in those images has a brightness, a distance, and a rough age. By counting how many galaxies appear at different brightness levels and redshifts, you can build something called a luminosity function, a mathematical description of how common galaxies of different brightness are at different times in cosmic history. The deep fields had already revealed the bright end of that distribution very well. Consolis and his colleagues wanted to know what was happening at the faint end, below the threshold where Hubble could reliably see. The trick is that the shape of the luminosity function is not random. It is tied to how structure grows in an expanding universe filled with dark matter and gas. Cosmological simulations, which evolve billions of particles and gas cells forward from early times, predict how many small dark matter halos form, how often they merge, and how efficiently they turn gas into stars. By comparing these simulations with the observed deep field galaxies, you can infer how many faint systems must exist, even if they are too dim or too diffuse to appear in the images. Another key idea sits at the heart of all deep observations. When you look farther into space, you are also looking back in time. Light from a galaxy 10 billion light-years away left it when the universe was young, when matter was more densely packed and small structures were just beginning to form. In that era, there were many more tiny galaxies and proto-galaxies flickering into existence. Over billions of years, these small systems tended to collide and merge, building up the larger spirals and ellipticals we see around us today. That means that if you want to know how many galaxies the universe has contained over its history, you must pay attention to those early times. The deep fields are crucial here because they contain galaxies at many different look-back times in a single frame. The team used this layered view to reconstruct how the number of galaxies per unit volume changed as the universe aged. They found that the galaxy population was much richer in the past, especially at the faint end where Hubble begins to go blind. To fill in the missing galaxies, they extrapolated the luminosity functions beyond the detection limits. This is like extending a graph beyond the points you have actually measured, guided by the trend you see and by what simulations predict. It is a risky move if you push it too far, but the physics of structure formation gives you guardrails. If the number of faint galaxies rose too steeply, for example, it would contradict what we know from the cosmic microwave background or from the total amount of starlight observed in the infrared background. Within those constraints, you can estimate how many undetected galaxies are likely hiding below the noise. When those hidden galaxies were added to the census, the numbers ballooned. Instead of a few 100 billion, the calculations suggested that the observable universe had hosted on the order of 2 trillion galaxies over its history. Many of these would have been small, faint systems in the young universe that later merged into larger structures. In other words, if you could rewind cosmic time and fly through the universe when it was only a few billion years old, you would see a sky far more crowded with tiny galaxies than we observe today. This was a profound shift in perspective. The famous 2 trillion number does not describe a universe full of 2 trillion well-formed Milky Way clones floating around right now. It describes an evolving population, a cosmic family tree in which countless small branches have been eaten or absorbed by bigger ones. The galaxies we catalogue today are the survivors and descendants. Behind each bright spiral or giant elliptical lies a graveyard of smaller ancestors that no longer exist as separate systems. There is another subtle twist. Because of the finite speed of light and the expansion of space, there is a horizon beyond which we can never see. The observable universe is the bubble defined by all the light that has had time to reach us since the Big Bang. The 2 trillion estimate deliberately applies only to that bubble. It does not count galaxies in regions of space whose light is forever out of reach. Depending on the true size and shape of the entire cosmos, the total number of galaxies could be enormously larger than any number we can infer from observations. Even inside our observable bubble, the count is not carved into stone. The analysis that produced 2 trillion makes assumptions about the faintest galaxies and about how efficiently stars form in tiny dark matter halos. Different models of feedback from supernovae and black holes, different guesses about how gas cools and is blown out of small systems, can change the number of predicted faint galaxies. The deep field data provide powerful anchors, but there is still room for disagreement at the edge of observability. And then there is the fact that we now have new eyes on the sky. The James Webb Space Telescope, operating in infrared wavelengths, has already found surprisingly bright and massive candidate galaxies at very early times, closer to the Big Bang than many models expected. If some of those turn out to be real, they may imply different histories for galaxy formation and may alter how we extrapolate the faint population. Future wide-field surveys from space and from giant ground-based telescopes will map larger volumes of the universe in far greater detail, tightening the uncertainties. So when we say the universe contains around 2 trillion galaxies, what we really mean is this. When you combine the deepest images from Hubble with our best theories of cosmic evolution, and when you account for the swarms of faint systems we know must lurk below our detection limits, you arrive at a number of that order for the galaxies that have lived within our observable bubble. It is a synthesis, not a simple head count, and it carries the fingerprints of every assumption built into our models. This might sound disappointing if you were hoping for a precise, final tally, yet there is something beautiful about it. The 2 trillion figure is not just a label slapped on the universe. It is a summary of how much we have learned about structure formation, dark matter, star formation, and cosmic history. As our instruments and models improve, the number will be revised. It may go up or down. What matters more is the process. The way we move from a grain of sand-sized window in the sky to a coherent story about the population of galaxies across the cosmos. In the next part, we will take a step back from these details and look at the stage on which all of this unfolds. We will explore the size of our observable bubble, the strange way expansion stretches space, and what the phrase observable universe really hides. Only then can we see how our galaxy count fits into the wider structure of the cosmos, and how much lies forever beyond our reach. When astronomers say observable universe, it sounds like a grand, all-inclusive term, almost as if we have a complete map of everything that exists. In reality, that little word observable is a huge disclaimer. It means something very specific. Not all that exists, not even all that once existed, just the part of the cosmos whose light has had enough time to reach us since the beginning of the universe. Our famous 2 trillion galaxy number lives entirely inside that bubble. Everything outside it is invisible by definition. To see why this matters, start with something familiar. The Sun is about 150 million kilometers away. Light from its surface takes a little over 8 minutes to reach Earth. That means when you look at the Sun through a safe filter, you see it as it was 8 minutes ago. The nearest star beyond the Sun, Proxima Centauri, is so far away that its light takes more than 4 years to get here. You never see Proxima as it is now. You see it as it was 4 years in the past. Push that idea outward and it becomes astonishing. The Andromeda Galaxy sits about 2.5 million light-years away. The light in your telescope tonight left its stars when early humans had not yet appeared on Earth. Distant galaxies in the Hubble Ultra-Deep Field are seen as they were more than 10 billion years ago, when the universe was young and messy. Astronomy is always mixed with archaeology. Every line of sight is also a timeline. The universe itself has an age, based on measurements of the cosmic microwave background and the expansion rate. The best current estimate is that it is about 13.8 billion years old. That age sets a naive limit on how far we can see. You might think that the most distant light we could receive would be 13.8 billion light-years away. After all, how could light travel any farther than the time available? That guess turns out to be wrong for a subtle reason. Space itself has been expanding while the light has been in transit. Imagine you are standing on a rubber sheet with dots drawn on it. If you stretch the sheet, the dots move farther apart even though they are not walking anywhere. The universe does something similar on the largest scales. Galaxies far apart from each other are carried away by the expansion of space. While the light from a distant galaxy is on its long journey to us, the space between us and that galaxy keeps stretching. By the time the light arrives, the galaxy is much farther away than the distance the light actually travelled. Because of this, the region from which light has had time to reach us is larger than you might first expect. The radius of the observable universe today is about 46 billion light-years. That means the observable bubble is nearly 93 billion light-years across, even though the light we receive from its edge has been travelling for only 13.8 billion years. The path that light took is shorter than the current separation because the fabric of space expanded beneath it. Everything we can see lives inside this bubble. All the galaxies counted in deep surveys, all the clusters, all the filaments of the cosmic web that have left a trace in the form of light or other signals. Outside the bubble, the universe may continue in all directions. It might be finite or infinite. It might repeat patterns or contain regions with slightly different conditions. We simply do not know, because no signal from beyond that horizon has ever reached us, and, according to our current understanding of physics, never will. This has direct consequences for our galaxy tally. When we say there are around 2 trillion galaxies in the observable universe, the phrase "in the observable universe" is doing heavy lifting. We are counting the galaxies whose light is, in principle, reachable. That includes galaxies whose light left them billions of years ago and is only now arriving, and galaxies whose light we might receive in the future. It does not include galaxies that are already, and forever, beyond our cosmic horizon. To grasp the scale of what might lie beyond, imagine that the universe is much larger than our observable patch, like an endless ocean compared to a small island of visibility. If the cosmos on those larger scales is roughly similar to what we see inside our bubble, then there could be many, many more galaxies extending in every direction. Multiply the number of observable bubbles that would fit into a larger universe, and you easily reach numbers like tens of thousands of trillions of galaxies, or more. These are speculations grounded in our best models, but they remain speculations because we cannot test them directly. Even inside the observable bubble, there are edges in time as well as in distance. The cosmic microwave background is the afterglow of the hot early universe, emitted when the cosmos was only about 380,000 years old. Beyond that point, the universe was so dense and hot that light could not travel freely. We cannot see past that opaque wall with ordinary telescopes. Any galaxies that formed before a certain time are therefore permanently hidden from direct view. We infer their existence through theory, not through direct images. Add to this the accelerating expansion driven by what we call dark energy. Over the last few billion years, the rate at which distant galaxies recede from us has begun to increase. Far enough away, galaxies are carried away so quickly by the expansion of space that even light launched toward us now will never close the gap. These systems are already lost to future observers, even though their older light may still be reaching us from the past. In a sense, the observable universe is shrinking in terms of the regions we can ever hope to communicate with, even as we sit here counting galaxies. All of this paints a strange picture. The 2 trillion galaxies we talk about are not sitting in a static, transparent box. They live in an expanding, evolving, partly hidden cosmos. Some are already receding beyond the point where new light from them can ever reach us. Others have long since merged together, so that the ancient galaxies we see in deep images no longer exist as separate objects today. The observable universe is a moving target, changing with time as light from new regions arrives and other regions slip beyond our reach. Yet within this shifting, finite bubble, we can do something remarkable. We can measure, model, and understand enough of what is going on to build a coherent story about structure on the largest scales. We can map filaments and voids, weigh clusters with gravitational lensing, and stitch together the life history of galaxies across billions of years. Our galaxy count is one of the summaries of that story, a headline that hides a great deal of nuance. In the next part, we will zoom out from individual galaxies, and even from the bubble itself, to look at how matter is woven into a vast, three-dimensional network. We will trace our address from the Milky Way to the local group, to the Virgo cluster, and out into the grand architecture of the cosmic web. Along the way, the 2 trillion galaxies will turn from abstract points into beads strung along immense filaments of structure, giving us a new sense of where we live in this bewildering, beautiful universe. So far, we have talked about galaxies as if they were scattered through space like birds in a vast sky. That picture is comforting, but it is wrong. On the largest scales, the universe is not a random spray of galaxies. It is a structure, a pattern, a kind of three-dimensional foam where matter gathers along invisible strands and leaves behind enormous, empty regions. Astronomers call this pattern the cosmic web. To understand our place in it, and to see what those 2 trillion galaxies are really doing, we need to zoom out and look at the architecture of the universe itself. Let us start close to home, and then work our way outward. The Milky Way does not live alone. It is part of a small neighbourhood called the local group. This is a collection of more than 50 galaxies that are all gravitationally bound to each other. The 2 heavyweights are the Milky Way and the Andromeda Galaxy, each with its own family of dwarf companions. The Triangulum Galaxy is a smaller but still significant member. Around them swarm dozens of faint dwarfs, some barely more than smudges of starlight. Together, all of these galaxies move through space as a loosely bound flock. If you zoom out further, the local group itself is just one member of a much larger association called the Virgo supercluster. The heart of this region is the Virgo cluster, a dense knot of more than 1,000 galaxies roughly 50 million light-years away. The local group sits out in the suburbs of this cluster, not in the crowded downtown. For decades, astronomers thought of Virgo as the main landmark in our cosmic address. Then better data on galaxy motions revealed an even grander pattern. In 2014, a team of researchers proposed the name Laniakea, which means immense heaven, for a vast supercluster that includes Virgo, the local group, and many other galaxy clusters. Instead of defining this region by counting galaxies in a box, they traced the flow of matter. By mapping the peculiar motions of galaxies, motions above and beyond the general expansion of the universe, they could see how gravity was pulling them. The results showed that our local group and our neighbouring clusters all flow toward a common gravitational basin. That basin, and the web that feeds it, form the Laniakea supercluster. When you look at a computer simulation of this region, the cosmic web appears as a tangle of filaments where galaxies and clusters lie like beads on strings. Between the filaments are immense voids, roughly spherical regions with very few galaxies inside. The pattern resembles a foam of soap bubbles frozen in mid-pop. Most of the volume of the universe is actually in these voids, vast darknesses hundreds of millions of light-years across, where only a handful of galaxies drift. The bright, busy regions where clusters live are thin surfaces between these holes. One of the most famous of these empty regions is the Bootes void. It is more than 200 million light-years across and contains far fewer galaxies than you would expect from an average patch of that size. When it was first discovered, it seemed like an insult to the idea of a crowded universe. How can a cosmos with 2 trillion galaxies also contain a region this empty? The answer is that the universe is not uniform on smaller scales. It is like a city. There are downtowns and there are quiet outskirts, packed freeways and lonely backroads. The cosmic web forms because of tiny fluctuations in the density of matter in the early universe. Right after the Big Bang, the cosmos was almost perfectly smooth, but not quite. Some regions were slightly denser than others. Gravity amplified those differences over billions of years. Denser regions pulled in more matter and grew into filaments, walls, and nodes. Less dense regions lost matter and became voids. Dark matter played the leading role, providing the bulk of the gravitational pull. Ordinary matter, the kind that makes stars and planets and you, followed along, collecting in the same places. From the perspective of galaxy counting, this web has important consequences. Galaxies are not sprinkled evenly through the observable universe. They cluster along the filaments. If you point your telescope along a dense filament, you will see many more galaxies than if you look into a void. This is why cosmic variance appears in deep surveys. 2 small patches of sky at the same depth can show very different galaxy counts simply because one passes through more structure than the other. To get a reliable number for the whole universe, you must sample many directions and average across the network. Our own Milky Way lies on the edge of one of these filaments, perched near the boundary of a local void. That nearby emptiness is sometimes called the local void. It is a region adjacent to our local group that contains far fewer galaxies than the surrounding areas. The presence of this void subtly influences the motion of nearby galaxies, just as the presence of a valley changes how water flows across a landscape. We tend to imagine ourselves at the centre of things, but gravitationally, we live on the slope of a larger structure, drawn towards some regions and away from others. When astronomers create maps of the nearby universe, they often show slices through the cosmic web, with each galaxy marked as a dot. What looks at first like random noise quickly reveals structure. You see elongated chains of dots stretching across the plot, clusters where many dots bunch together, and great arcs of emptiness where almost no dots appear. In 3 dimensions, these chains are the filaments, the clusters are massive nodes, and the empty regions are voids. The pattern looks almost organic, as if the universe grew veins and capillaries. This architecture does more than arrange galaxies, it shapes their lives. Galaxies in dense clusters collide and merge more often. They can be stripped of gas as they plunge through hot intracluster plasma, quenching their star formation. Galaxies in filaments have more moderate interaction histories. Those in voids can evolve in relative isolation, keeping their gas longer and continuing to form stars at a steady pace. The cosmic web is not just a backdrop, it is the stage and the script for galaxy evolution. Thinking about the universe this way changes how we interpret our 2 trillion galaxies. They are not merely a count of isolated islands scattered across a black ocean. They are the luminous knots on an intricate cosmic net, each one telling us where the underlying dark matter resides and how matter has flowed over billions of years. When we measure how many galaxies occupy different environments, from dense nodes to quiet voids, we are really probing how the web itself is woven. In the next part, we will narrow our focus again, this time not on where galaxies live, but on which ones we can actually see. You will meet the hidden majority that slips through our observational nets, the faint dwarfs and ultra-diffuse ghosts, the galaxies buried behind the Milky Way, and those whose light has shifted into wavelengths our older instruments could barely detect. Only by understanding that unseen population can we appreciate how incomplete our view still is, even with all of our maps of the cosmic web. Up to now, our story has been dominated by showpieces, beautiful spirals, giant ellipticals, colourful colliding systems that look great in posters and thumbnails. But those galaxies are like the celebrity guests at a party. They draw the cameras, yet they are massively outnumbered by quieter, less visible guests. The universe is filled with galaxies that are too faint, too spread out, too buried in dust, or too shifted in colour for our eyes and many of our telescopes to notice. When astronomers say we might be missing most of the galaxies that exist, they are talking about this hidden majority. The first big culprit is something called surface brightness. Imagine two billboards that use the same number of light bulbs. One packs all the bulbs into a tight logo, the other spreads them across a huge area. Up close, both seem equally bright, but from far away the compact sign pops while the spread out one fades into the background. Galaxies work the same way. A small galaxy with many stars crammed into a tight region can shine strongly against the black of space. A galaxy with the same total starlight smeared over a much larger disk becomes ghostly and hard to detect. This is where ultra-diffuse galaxies come in. These strange systems can be as wide as the Milky Way, yet have only a tiny fraction of its stars. Picture a city that covers the same area as a normal metropolis, but has only a few streetlights scattered across it. In deep images, ultra-diffuse galaxies look like barely there clouds. Their light per unit area is so low that they almost blend into the noise of the sky. You can stare straight at one in a raw image and never realise it is a galaxy until you stack exposures or use careful processing. Some ultra-diffuse galaxies appear to sit inside massive dark matter halos, much more massive than you would guess from their meagre starlight. Others seem oddly deficient in dark matter, raising awkward questions for our models of how galaxies form. Either way, they highlight how biased our galaxy catalogues can be. If an entire Milky Way-sized system can hide as a faint smudge, how many smaller, even lower surface brightness galaxies are simply slipping through our nets? Then there are the tiny dwarfs. At the extreme end, some known dwarf galaxies contain only a few thousand stars. Compare that with the hundreds of billions in the Milky Way. These ultra-faint dwarfs orbit larger galaxies like our own, embedded in dark matter halos. But their visible portions are so sparse that they are almost impossible to pick out from the sea of foreground stars. Astronomers often discover them by noticing a subtle overdensity of similar stars that move together, a pattern so delicate that it took modern surveys to reveal it. For every dwarf we have found around the Milky Way, simulations predict there should be many more. Some may have already been shredded into stellar streams, others are simply too faint for our current instruments. That means, even in our immediate neighbourhood, we do not yet have a complete census of galaxies. If we are undercounting the tiniest companions near us, it is almost certain we are missing huge numbers of similar dwarfs further away, where each star is fainter and harder to measure. On larger scales, our own galaxy creates an enormous blind spot. The Milky Way is a disk of stars, gas and dust. When we look along the plane of that disk, we see a crowded band of stars arcing across the sky. It is beautiful to the eye, but terrible for deep galaxy hunting. Dust clouds absorb and scatter light from background galaxies. Bright foreground stars create glare and optical artifacts. The region where distant galaxies are heavily obscured by our own is sometimes called the zone of avoidance. It is not truly empty, it is just hidden behind the messy foreground of our home. Infrared and radio telescopes can peer through some of that dust, revealing galaxies and clusters lurking behind the Milky Way. Those discoveries show that the cosmic web continues across the plane of our galaxy. Any galaxy count that ignores these buried structures would be incomplete. Yet even with modern technology, this part of the sky remains harder to survey than the clear regions above and below the galactic plane, so our maps there are still patchy and biased. Distance adds another layer of invisibility. As the universe expands, light from remote galaxies is stretched to longer wavelengths. This redshift moves ultraviolet and visible light into the infrared. Hubble, which excels at visible and ultraviolet wavelengths, sees only those very distant galaxies whose light is still strong enough in its available bands. Many of the smallest, earliest systems have their light shifted so far that they are effectively invisible to Hubble. They glow in wavelengths the telescope was not built to see. Infrared observatories such as the James Webb Space Telescope are beginning to uncover some of this hidden population. Webb can detect galaxies whose light has been stretched deep into the infrared, reaching back to very early times. Already, it has found galaxies that seem surprisingly massive and bright when the universe was less than 1 billion years old. These discoveries are forcing astronomers to rethink how quickly structure assembled. At the same time, they raise the possibility that even the 2 trillion number may need revision as we account for entire populations of early galaxies we were blind to before. Noise and confusion also play their part. In deep images, light from galaxies overlaps, stars blend into galaxy cores, and faint smudges can be mistaken for statistical fluctuations. Automated detection software must decide which blobs are real objects and which are noise. Set the detection threshold too high and you miss real galaxies. Set it too low and you fill your catalogue with false positives. Astronomers tweak these algorithms carefully, but they can never be perfect. The faintest real galaxies live right on the edge of what these methods can reliably pick out. Even when a faint galaxy is detected, measuring its properties is difficult. If you do not know its distance well, you cannot be sure how intrinsically faint or small it really is. Errors in distance turn into errors in luminosity and size, which then feed back into the statistics used to estimate the total galaxy population. The hidden majority is not only hidden in images, it is hidden in the uncertainties of our measurements and in the assumptions of our models. All these factors mean that our telescopes act like biased surveyors. They favour bright, compact, nearby and unobscured galaxies. They struggle with faint, spread out, distant and buried ones. When astronomers correct for these biases, they are essentially trying to guess how many galaxies lie in the regions of parameter space where our instruments perform poorly. That guess is informed by physics and simulations, but it remains a guess. The 2 trillion estimate is heavily weighted by populations we have scarcely seen. There is something humbling about this. The iconic galaxy images that circulate online are not a representative sample of the universe. They are the best behaved students in the cosmic classroom. Behind them is a vast crowd of odd, quiet, half-formed or half-destroyed systems that rarely make the headlines. From the perspective of a full cosmic census, those misfits matter more than the stars of the show because they dominate the numbers and hold crucial clues about how structure builds up from the bottom. In the next part, we will turn from the galaxies themselves to the machines we use to see them. We will explore how telescopes act as extensions of our senses, how different wavelengths reveal different layers of structure, and how the next generation of observatories may finally bring parts of this hidden majority into view. Only by understanding our tools can we judge how much of the universe we are truly seeing, and how much still lies in the dark. From the ground, under a dark sky, you see a thin band of the Milky Way and a scattering of stars. From space, with the right tools, that same sky explodes into thousands of galaxies in a patch no bigger than a grain of sand. The difference is not that the universe changes, the difference is in our senses. Telescopes are not just big metal tubes, they are artificial extensions of human perception, designed to hear whispers our eyes were never built to catch. To understand our galaxy counts, we have to understand these machines and the limits they carry. Your eyes work in a narrow slice of the electromagnetic spectrum, a small band we call visible light. Telescopes can be built to pick up many other kinds of light: radio waves, infrared, ultraviolet, X-rays, gamma rays. Each type reveals different parts of galaxies and different populations of galaxies. When we talk about deep images from Hubble or James Webb, We are really talking about carefully tuned senses, each with its own strengths and weaknesses. Our picture of the galaxy population is stitched together from these partial views. Hubble was our first truly iconic eye in space. Launched in 1990 and repaired in orbit a few years later, it was designed to see mainly invisible and ultraviolet light. Its mirror is 2.4 meters across, which is small compared to some ground-based telescopes, but its vantage point above the atmosphere makes up for that. Without the blur and twinkle caused by air currents, Hubble can resolve fine details and take long exposures without the sky background changing wildly under it. For galaxy counts, Hubble brought two crucial abilities: sharpness and patience. Sharpness meant that faint galaxies did not smear into indistinct blobs. Patience meant that Hubble could stare at one patch of sky for many hours, stacking exposure after exposure until the faintest detectable galaxies slowly rose above the noise. The Hubble Deep Field and Ultra Deep Field were demonstrations of those strengths. They showed us that even in visible light alone, the sky is crowded with galaxies that ground telescopes could barely hint at. But visible light is only one channel. As the universe expands, light from very distant galaxies is stretched, shifted toward redder wavelengths. Some of that light moves out of the visible band and into the infrared. Dust in galaxies also absorbs visible light and re-emits it in the infrared. If you look only with visible, sensitive instruments, you miss many of the earliest galaxies and many dusty, star-forming systems that glow brightly in infrared. This is where the James Webb Space Telescope comes in. James Webb orbits near a gravitational balance point called the second Lagrange point, about 1.5 million kilometers from Earth. There it can keep its back to the Sun and Earth, shielded by a multi-layer sun shield that lets its instruments cool down to extremely low temperatures. Cold detectors are crucial for infrared astronomy. Any warmth in the telescope itself would swamp the faint infrared signals from distant galaxies. Webb was built from the ground up as a cold, infrared optimized eye on the cosmos. Its mirror is larger than Hubble's, about 6.5 meters across, made of hexagonal segments that unfolded in space. This bigger collecting area and infrared sensitivity allow Webb to see galaxies whose light has been stretched almost beyond Hubble's reach. In its first images, Webb revealed rich structures in galaxies we already knew, and then went further, picking out candidate galaxies from times close to the end of the cosmic dark ages. Some of these appear surprisingly bright and massive for such early times, forcing theorists to revisit their models of how quickly galaxies can grow. From the perspective of galaxy counts, Webb does two things at once. It adds new galaxies to our catalogues, especially at high redshift, and it challenges our assumptions about the faint population we used to infer from Hubble alone. If early galaxies are more numerous or more massive than we thought, that affects how we extrapolate to the undetected one. On the other hand, if some of the earliest candidates turn out to be more ordinary systems, misidentified by initial data, that will tighten the bounds on the true population. In either case, the numbers are in motion. Space telescopes get the glory, but giant observatories on the ground also play a central role. Telescopes like Keck in Hawaii and the Very Large Telescope in Chile have mirrors 8 to 10 meters across. They use adaptive optics, deformable mirrors that shift hundreds of times per second to cancel out the blur introduced by Earth's atmosphere. The result is ground-based images with sharpness that rivals or even surpasses Hubble in some wavelengths. These facilities can scan large areas of sky, measure detailed spectra for many galaxies at once, and track how galaxies move and interact. Spectroscopy is like taking light from a galaxy and passing it through a prism. The resulting spectrum shows absorption and emission lines that act as fingerprints of the elements present and as rulers for measuring redshift. From these lines, astronomers can determine how far away a galaxy is, how fast it is moving, how quickly it is forming stars, and even how much dust and gas it contains. None of that comes from images alone. When we build a galaxy census, images tell us who is there, spectra tell us who they are, and where and when they live. Upcoming ground-based projects will push this even further. The Vera Rubin Observatory, for example, will repeatedly image the entire visible sky with a wide-field camera. Its main mission is to study how things change over time, but its deep, repeated exposures will also uncover huge numbers of faint galaxies, especially dwarfs and ultra-diffuse systems that were missed before. Extremely large telescopes, with primary mirrors 30 meters across or more, are being planned and built. These will resolve fine structure in distant galaxies and measure spectra for objects that are now just beyond our reach. In space, the Nancy Grace Roman Space Telescope is being designed as a wide-field surveyor. Compared to Hubble, Roman will have a field of view that is hundreds of times larger while maintaining sharp resolution. Think of it as a Hubble-class eye with a panoramic lens. For galaxy counts, this means we will not only have tiny ultra-deep pencil beams through the universe, but also broad, deep mosaics that can map large fractions of the sky. That will reduce the impact of cosmic variance and give a more representative sample of galaxy environments. Each of these instruments is sensitive in particular wavelength bands and is built with certain trade-offs between depth, area, and resolution. Together, they form a network of artificial senses. Some look deep and narrow, some scan wide and shallow. Some focus on visible light, others on infrared, radio, or X-rays. When astronomers talk about the known galaxy population, they are talking about the union of everything these senses have revealed so far. When they estimate the unknown population, they are leaning on models guided by what these tools can and cannot see. It is tempting to imagine that there is a finishing line, a future telescope that will finally see all the galaxies and lock in a final number. The reality is more subtle. Each new generation of instruments opens a window onto previously hidden structures and forces us to revise our understanding. We are not marching toward a static census. We are learning how the universe presents itself in different colours of light, and how each colour tells a different part of the story. In the next part, we will step away from the statistics and meet some galaxies up close. We will visit our own Milky Way, our neighbour Andromeda, giant ellipticals, irregular companions, and some of the strangest systems ever found. By turning the abstract count of 2 trillion into a cast of individual characters, we can feel more directly what that number actually represents. Not a sea of identical dots, but a vast menagerie of unique worlds and histories woven into the same cosmic web. By now, 2 trillion galaxies might sound like just another big statistic. A huge number, impressive on paper, but hard to feel. So let us change the angle. Instead of looking at the universe as a cloud of anonymous dots on a graph, we will meet some of those dots up close. We will walk through a handful of galaxies as if they were people at a party, each with their own personality, scars, and history. Once you know a few of them well, the idea of trillions becomes less abstract and more like a city filled with unique neighbourhoods. We start at home. The Milky Way is a barred spiral galaxy, a flat disk of stars with a central bar-shaped structure and winding arms. Our Sun is just one of hundreds of billions of stars orbiting in that disk, about 2/3 of the way out from the centre. The galaxy is roughly 100,000 light-years across, wrapped in a much larger halo of dark matter and scattered ancient stars. Inside the disk, there are star-forming regions where gas clouds collapse into new suns, and older, quieter zones where stars drift in stable orbits. At the core of the Milky Way lurks a supermassive black hole called Sagittarius A star. It holds the mass of millions of suns in a region smaller than our solar system. We know it is there because stars near the centre whirl around an invisible point, their orbits betraying a huge concentration of mass. Material falling toward this black hole can heat up and flare, but right now it is relatively quiet. The Milky Way is not a raging quasar. It is more like a big city with a calm downtown and lively suburbs. Step outside our home and the next major landmark is Andromeda. This galaxy is bigger and more massive than the Milky Way, another spiral with a bright core and sweeping arms. It lies about 2.5 million light-years away, close enough that you can see it as a faint smudge with the naked eye from a dark site. Andromeda and the Milky Way are not just neighbours, they are on a slow collision course. In a few billion years, their mutual gravity will pull them together in a grand merger that will reshape both galaxies into a single, larger system. That future collision reminds us that galaxies are not static islands. They are part of a slow dance. The Triangulum galaxy, a smaller spiral in our local group, is also involved in this choreography. Star streams and warped disks in all three systems hint at past interactions. If you could speed up cosmic time, you would see galaxies pass through one another, tear off tidal tails, ignite waves of star formation, and finally settle into new shapes. Our serene pictures of spirals and ellipticals are single frames from that ongoing movie. Farther out in the Virgo cluster, we meet a very different character. Messier 87 is a giant elliptical galaxy, a huge ball of old stars with little cold gas and little new star formation. It is home to one of the most massive known black holes, the one whose silhouette was imaged by the Event Horizon telescope. This black hole powers a jet, a narrow beam of energetic particles that shoots out of the galaxy and stretches thousands of light years into space. In visible light, M87 looks smooth and featureless. At radio wavelengths, it blazes with the signature of its central engine. If spiral galaxies are like grand pinwheel cities, ellipticals like M87 are more like ancient, densely packed metropolises. Most of their stars formed long ago. Many spirals that drift into clusters eventually lose their gas and are transformed into ellipticals through mergers and harassment by hot intracluster gas. The galaxy count in a cluster is not just a list of separate citizens. It is a record of past mergers, cannibalism, and reshaping driven by the crowded environment. Now we detour to some of the more photogenic spirals. The Whirlpool galaxy, also known as Messier 51, is a classic grand design spiral with two prominent arms. It is interacting with a smaller companion, which has triggered waves of star formation that light up its arms with bright blue clusters and pinkish nebulae. The Sombrero galaxy has a bright central bulge and a prominent dust lane that makes it look like a hat in silhouette. Centaurus A is a warped, disturbed galaxy that shows a dark band of dust cutting across a bright elliptical body, the aftermath of a past merger with a smaller disk galaxy. Then there are the truly odd shapes. The Cartwheel galaxy looks like a bright ring with spokes, formed when a smaller galaxy plunged through a larger disk and sent out a ripple of star formation. Hoag's object is an almost perfect ring galaxy with a yellowish core and a blue outer ring, separated by a gap. The Tadpole galaxy has a bright head and a long tail of stars, the result of tidal forces pulling material away during a close encounter. These galaxies are the drama queens of the universe. They remind us that collisions are not rare accidents, but a standard part of galactic life. On much larger scales, some galaxies seem almost defined by their radio structures. Alcyonius, for example, is a radio galaxy with enormous lobes that stretch hundreds of millions of light years. In visible light, its host galaxy is unremarkable. In radio observations, it becomes a giant, with jets that inflate vast bubbles in the intergalactic medium. Systems like this show that the influence of a galaxy can extend far beyond its visible stars, sculpting the gas in the cosmic web and feeding energy back into its surroundings. At the opposite end of the spectrum, in both size and brightness, are the dwarf galaxies we met earlier. The Large and Small Magellanic Clouds, two irregular dwarf companions of the Milky Way, are visible in southern skies as hazy patches. They are close enough that individual star-forming regions can be studied in detail, such as the Tarantula Nebula, a huge nursery of massive stars in the Large Magellanic Cloud. Much smaller dwarfs, like Segway 2, barely rise above the glow of our own galaxy, yet they carry clues about dark matter and the earliest stages of galaxy formation. Once you have this cast of characters in mind, 2 trillion galaxies does not mean 2 trillion copies of the Milky Way. It means 2 trillion variations on these themes and many others. Spirals in all degrees of neatness and distortion, ellipticals from modest bulges to cluster-dominating giants, irregular dwarfs that never quite settled into a shape, ghostly ultra-diffuse systems that hover at the edge of detection, radio-loud monsters with jets, quiet disks gently forming stars, galaxies in the act of tearing each other apart. The statistics we use to describe the universe draw from this zoo. When astronomers talk about the distribution of galaxy masses, they are summarizing how many Milky Way-sized systems exist compared to dwarfs and giants. When they describe the fraction of spirals versus ellipticals, they are summarizing the balance between calm disks and merger products. Each point on a graph or term in an equation stands in for many individual galaxies like the ones we have visited. There is also a subtle emotional shift that happens when you think of galaxies as characters rather than dots. You start to feel the universe less as an empty stage with scattered props, and more as a living history. Each galaxy has a biography written in its stars, its gas, its dark matter halo, and its environment. Some biographies are quiet and steady. Others are filled with violent events. 2 trillion galaxies means 2 trillion long stories, most of which no one will ever read in detail, but all of which contribute to the pattern we observe. In the next part, we will return to that pattern and focus on how these stories change the galaxy count over time. We will follow galaxies from their birth in collapsing clouds, through growth by mergers and accretion, to the slow decline of star formation in the distant future. Along the way, you will see why the number of galaxies is not fixed, and why the universe of the past, present, and far future each has its own different census. When we talk about 2 trillion galaxies, it is easy to imagine a fixed population, a static list of island universes hanging in space, each with a permanent name tag. The reality is far more restless. Galaxies are born, they grow, they collide, and they fade. The cosmic census is not a single number etched into reality. It is a moving target that changes as the universe ages. Every galaxy story begins in the early universe, when matter was almost, but not quite, evenly spread out. Slightly denser regions of dark matter began to pull in more mass through gravity. These clumps grew into dark matter halos, invisible cocoons that would later host galaxies. Gas fell into the potential wells of these halos, compressed, cooled, and eventually formed the first stars. At this stage, the universe contained many small halos, each hosting only a modest collection of stars. Those early galaxies were not delicate. Their stars were massive, hot, and short-lived, flooding their surroundings with intense radiation and powerful winds. Supernova explosions stirred and sometimes expelled gas, regulating how quickly new stars could form. Some halos stayed small, forming only a few generations of stars. Others began merging with neighbours, creating larger structures with deeper gravitational wells that could hold on to more gas. As mergers proceeded, the galaxy population shifted toward fewer, larger systems. A merger between 2 galaxies is not like a head-on car crash. Stars inside them are so far apart that direct collisions between individual stars are extremely rare. Instead, the gravitational pull of each galaxy reshapes the orbits of stars in the other. Gas clouds slam into one another, compress, and trigger bursts of new star formation. Over hundreds of millions of years, the 2 galaxies stretch, warp, and eventually settle into a new shape. A neat spiral may turn into a distorted mess, and finally relax into an elliptical galaxy. Astronomers talk about major and minor mergers. A major merger involves 2 galaxies of comparable mass. These events can completely transform their participants, scrambling disks into spheroids and igniting intense starburst episodes. Minor mergers involve a large galaxy and a much smaller companion. In those cases, the big galaxy often survives with its overall structure intact, while the smaller one is shredded and absorbed. The Milky Way is currently in the process of digesting several dwarfs in just this way. We can see the remains of past meals in our own galaxy. Long, thin streams of stars arc through the halo of the Milky Way, the stretched remnants of ancient dwarfs that wandered too close. The Sagittarius dwarf galaxy, for example, has been pulled apart over billions of years, leaving a looping trail of stars. These streams act as fossils of past mergers, telling us that our galaxy has grown not only by forming new stars in its own gas, but also by cannibalizing smaller neighbors. Each of those neighbors once counted as its own galaxy in the cosmic census. The future collision between the Milky Way and Andromeda will be a major merger. In a few billion years, their mutual gravity will draw them together. Their disks will interpenetrate, their stars will be flung onto new orbits, and their gas will pile up and ignite enormous bursts of star formation. After several close passages and a final coalescence, the result will likely be a single, massive, elliptical-like galaxy, sometimes nicknamed Milkomeda. Where the census once listed 2 large spirals, it will record 1 giant descendant. On smaller scales, mergers can create entirely new galaxies. When 2 big galaxies interact, tidal forces rip out long tails of gas and stars. Portions of these tidal tails can collapse under their own gravity, forming tidal dwarf galaxies. These systems are newborn in one sense, but their stars come from older parents. Counting them raises interesting questions. Are we adding a new galaxy to the census, or merely reshuffling stars that were already part of another system? Over cosmic time, this process of growth and consolidation has a clear direction. In the early universe, there were many more small galaxies per unit volume than there are today. As time passes, more of those small systems either merge into larger ones or are stripped and destroyed. The total number of distinct galaxies decreases, even as the mass of the surviving galaxies increases. The universe trades quantity for size. Fewer islands, but each one larger and more massive. Star formation follows its own life cycle within this broader story. Galaxies begin rich in cold gas, the raw fuel for new stars. As stars form and die, they enrich the gas with heavier elements and stir it with winds and supernova shocks. Over billions of years, galaxies slowly convert their gas into stars. If they live in dense regions, interactions and hot cluster gas can strip their remaining fuel and shut down star formation. These galaxies fade into redder, quieter systems with little new activity. This slow decline is visible on the largest scales. Measurements of star formation history show that the universe was much more active in the past. There was a peak era when galaxies were forming stars at rates far higher than today. Since then, the average star formation rate per unit volume has dropped dramatically. In a universe with less gas forming fewer stars, future galaxies will gradually become dimmer as their massive stars burn out and only smaller, long-lived stars remain. Already, we can identify galaxies at many different stages of this life cycle. Some are blue, gas-rich, and bursting with new stars. Others are red and dead, with little cold gas and a population dominated by older stars. Some are undergoing mergers right now, their shapes distorted, and their centers lit by starbursts or active black holes. Others drift in quiet isolation in voids, evolving slowly. Each stage contributes differently to the total galaxy count and to how bright the universe appears in different wavelengths. In the extremely distant future, dark energy and accelerated expansion will add another twist. As galaxy groups and clusters become gravitationally isolated from one another, there will be fewer opportunities for new mergers across large distances. Within each bound region, like our local group, the remaining galaxies will eventually merge into a single enormous system. After that, the galaxy count on those scales will effectively drop to 1. Around that lone survivor will stretch a dark, expanding space from which no new galaxies ever arrive. All of this means that if you could take a snapshot of the universe at different epochs and count galaxies, you would get different answers each time. Shortly after the first galaxies formed, the count would be high, dominated by numerous small systems. At the present day, the count is lower, with more intermediate and large galaxies. In the far future, the count will drop again as structures merge and as expansion isolates each bound region. Our famous 2 trillion is a description tied to a particular era, not a timeless property of reality. From a human point of view, this might feel unsettling. We tend to like fixed numbers and clear categories. Yet the changing galaxy count is a sign that the universe is not just a backdrop, but an evolving story. Every merger, every burst of star formation, every dwarf that dissolves into a larger halo nudges the cosmic census. The population of galaxies is a living statistic, reflecting both the underlying physics of gravity and gas and the passage of time itself. In the next part, we will link this living statistic to an even more personal question. If there are trillions of galaxies, each with its own stars and planets. What does that imply about the chances for life and intelligence elsewhere? We will explore how galaxy numbers feed into estimates of habitable worlds, and why, despite the abundance suggested by our census, the universe still seems so eerily quiet. All through this journey, galaxies have been the stars of the show, but the real reason we care about galaxies is more intimate. Inside them live stars. Around those stars circle planets. On at least one of those planets, there is a species capable of building telescopes and wondering how many others are out there. When you hear that the observable universe may contain around 2 trillion galaxies, the next thought is almost automatic. How many worlds is that? And if there are so many, why does the universe feel so quiet? Let us start in our own backyard and then scale up. In the past few decades, astronomers have confirmed thousands of planets orbiting other stars in the Milky Way. These are called exoplanets. Many were found by watching stars for tiny dips in brightness when planets pass in front. Others were detected through small wobbles in starlight as orbiting planets tug on their host stars. When you correct for the biases of these methods, the conclusion is clear. Planets are not rare decorations. They are a standard part of star systems. One of the big questions is how many of those planets lie in the habitable zone of their stars. The habitable zone is the range of distances where a planet with the right atmosphere could have liquid water on its surface. Not too close and not too far. Around small, cool stars, the habitable zone is tucked in close. Around big, hot stars, it lies much farther out. Observations suggest that a significant fraction of Sun-like stars may host at least one roughly Earth-sized planet in their habitable zones. Take a conservative estimate. Suppose only a modest fraction of stars in the Milky Way have potentially habitable planets. Even then, given that our galaxy likely holds hundreds of billions of stars, you end up with tens of billions of possible Earth-like worlds in the Milky Way alone. Now remember that the Milky Way is just one medium-sized galaxy among perhaps 2 trillion in the observable universe. Multiply it out and you quickly reach numbers like 10 to the 20th or 10 to the 21st potentially habitable planets. That is a 1 followed by 20 or 21 zeros. These are not precise counts. They are rough extrapolations built on incomplete data and many assumptions. They do not include more exotic possibilities such as life in subsurface oceans on icy moons, or life based on chemistries very different from our own. Yet even a cautious estimate leads to an overwhelming sense of abundance. A universe filled with galaxies should be a universe filled with planets. A universe filled with planets should offer countless chances for life to arise, evolve, and maybe become intelligent. This makes the silence around us feel strange. We do not see unmistakable signs of advanced civilizations in the sky. No galaxy-wide engineering projects that block starlight in obvious patterns. No clear, repeating radio beacons that cut through the cosmic background. No enormous structures drifting across the stars. The Milky Way looks, as far as we can tell, like a normal galaxy. Our local neighbourhood seems quiet. When we look outward, the other galaxies look quiet as well. This is the heart of what is famously called the Fermi paradox. On one side, you have the apparent abundance of habitable real estate and the long age of the universe. On the other, the absence of clear evidence for anyone else. Physicist Enrico Fermi framed it in simple terms over lunch. Where is everybody? In a universe with so many galaxies and so much time, why do we not see visitors, signals, or visible signs of activity? There are many possible broad answers, none of them fully satisfying. One category of answers says life is rare. Maybe the steps from chemistry to simple life are incredibly unlikely. Perhaps the jump from simple cells to complex ones is a huge barrier. It could be that developing intelligence capable of technology is a fluke. In this view, the universe might be full of sterile rocks and lifeless oceans. Earth could be one of the few places where the chain of accidents lined up just right. Another category says life may be common, but technological civilizations are fragile or short-lived. Once a species discovers powerful technology, it also discovers new ways to destroy itself or wreck its environment. War, Runaway climate change or other self-inflicted problems could wipe out many civilizations long before they have the chance to spread among the stars. In that case, the galaxy might be dotted with the ruins of brief, brilliant flashes of intelligence that left little trace on cosmic scales. A third set of ideas suggests that advanced civilizations are out there, but choose not to make themselves obvious. They might be following their own version of a prime directive, avoiding interference with younger societies. They might be communicating in ways we do not recognize, using neutrinos or gravitational waves, or something even more exotic instead of radio. Their structures might blend into natural astrophysical phenomena so well that we do not notice them. To us, their most impressive feats might look like ordinary galaxies and stars. Then there is the possibility that we are simply looking in the wrong way. Our searches for signals have covered only a tiny fraction of the possible frequencies, directions, and times. Imagine trying to decide whether a city is inhabited by listening with a microphone for an hour in one alley. The fact that you do not hear a shout does not prove the city is empty. It just means you have barely begun to check. Our tools are improving, but as of now, our exploration of the cosmic haystack has barely scratched the surface. The numbers we have been discussing deepen the tension. 2 trillion galaxies, each with hundreds of billions of stars, each star with a decent chance of having planets. Even if the odds of life were extremely low on any individual world, the sheer scale seems to favour many origins of life. Even if only a tiny fraction of those biospheres produced intelligence, you would expect some galaxies to host long-lived, far-reaching civilizations. Yet all the galaxies we see look, from a distance, like natural systems following the usual rules of physics. It is possible that this tension is an illusion created by our ignorance. Our estimates of habitable planets are crude. We do not yet know how often planets end up with stable climates, plate tectonics, magnetic fields, and long-term conditions suitable for complex life. We do not know how often life, once started, crosses key evolutionary thresholds. Until we understand those probabilities better, our extrapolations from galaxy counts to likely civilizations are guesses stacked on guesses. Still, the galaxy census gives the question of life a new frame. Instead of wondering whether there are other worlds at all, we can be confident that there are many. The mystery shifts from existence to contact. It becomes less a question of whether the universe has room for others, and more a question of what kinds of histories unfold on those other worlds, and why those histories have not yet intersected decisively with ours. From a human perspective, there is a strange mix of loneliness and connection in this picture. On the one hand, we may be rare, perched on a habitable world in a quiet corner of one galaxy among trillions. On the other, every galaxy we see, every faint smudge in a deep field, is a potential cradle for its own stories, its own experiments in chemistry and complexity. The galaxy count tells us that the cosmos is not short on opportunities. In the next part, we will move back from life and return to the invisible framework holding all of this together. We will look at dark matter, the unseen scaffolding that shapes where galaxies can form and how they cluster. You will see why our 2 trillion visible galaxies are only the luminous frosting on top of a much larger, darker structure that never quite turns fully to light. Up to this point, our story has treated galaxies as if they were built entirely from the things we can see: stars, gas, dust, light. But that is only the bright skin of a much larger body. Every galaxy we have met sits inside an invisible structure that outweighs its visible parts by a wide margin. This hidden component is called dark matter, and without it, the whole architecture of 2 trillion galaxies makes no sense. If we want to understand what we are really counting, we have to look at the scaffolding we cannot see. The first signs that something was missing came from the way galaxies spin. In the 1970s, astronomer Vera Rubin and her colleagues measured how fast stars orbit in the outer regions of spiral galaxies. According to the gravity of visible matter alone, stars far from the centre should move more slowly, the way planets in our solar system move more slowly as you go outward from Mercury to Neptune. Instead, the rotation curves stayed flat. Stars far out were racing around almost as fast as those in the inner regions. The simplest explanation is that there is more mass present than the stars and gas account for. Not a little more, several times more. This extra mass does not shine, does not absorb light, does not behave like ordinary gas or dust. It reveals itself only through gravity. Similar puzzles appeared in galaxy clusters. The galaxies themselves did not weigh enough to hold the cluster together at the observed speeds. Something unseen had to be providing additional gravitational glue. As more evidence accumulated, a picture emerged. Every galaxy lives inside a dark matter halo, a roughly spherical cloud of invisible mass that extends far beyond the visible edges of the disk or bulge. The stars and gas we see are like the bright core of an iceberg peeking above the surface of a dark ocean. The halo shapes how the galaxy rotates, how it responds to encounters, and how it sits within the larger cosmic web. Without dark matter halos, galaxies would not form in the numbers and configurations we observe. Gravitational lensing provides a striking confirmation of this invisible scaffolding. According to general relativity, mass bends space-time, and light follows curved paths through that warped geometry. When a massive cluster of galaxies lies between us and more distant galaxies, it can act like a lens, distorting and magnifying their images. By carefully measuring how background galaxies are stretched and smeared, astronomers can map the total mass in the lensing cluster, regardless of whether it shines. Those maps show that most of the mass in clusters is not in the visible galaxies or in the hot gas between them. It is in a smooth, extended component that behaves exactly like the dark halos predicted by simulations. On smaller scales, subtle statistical lensing effects called weak lensing reveal that even individual galaxies carry halos far more massive than their stars alone would suggest. The dark matter framework is not a guess tacked on at the edges. It is woven into every successful model of how structures grow. On the largest scales, the pattern of tiny temperature variations in the cosmic microwave background backs this up. The microwave background is the afterglow of the early universe, a snapshot of conditions when the cosmos was young and dense. The pattern of hot and cold spots encodes how much ordinary matter, dark matter, and dark energy were present at that time. When you run the numbers, you find that ordinary matter makes up only a small fraction of the total matter content. The rest behaves like dark matter, gravitating but not interacting with light. Now bring this back to galaxy counts. In cosmological simulations, dark matter halos form first as small seeds, then merge and grow into bigger halos. Ordinary gas falls into these halos and can cool and fragment into stars, creating visible galaxies. But not every halo manages this trick. In low-mass halos, the gas can be blown out by the first few generations of supernovae, or never cool efficiently in the first place. Some halos remain almost entirely dark, with little or no starlight to betray their presence. This leads to what is sometimes called the missing satellites problem. Early simulations predicted that a Milky Way-sized halo should contain hundreds or thousands of smaller subhalos, each a potential home for a dwarf galaxy. For a long time, we saw only a few dozen dwarf companions. Part of the solution was observational. As surveys improved, astronomers discovered many ultra-faint dwarfs that had been hiding in the background glow of our own galaxy. The census of satellites grew, but even now it appears that many predicted halos host no visible galaxy at all. In other words, there are more dark matter structures than there are luminous galaxies. When we count galaxies, we are counting only the halos that manage to light up. Many small halos are either too star-poor to qualify as galaxies or completely dark. Even some larger halos may have shut off their star formation so early that their remaining stars are too faint and diffuse for us to see at great distances. The population of dark halos is like a skeleton underneath the visible population, more numerous and more extended. This has a direct impact on how we interpret the 2 trillion figure. The number describes the galaxies that formed stars at some point in their history within halos above certain mass thresholds. It does not include the halos that never managed to host a visible galaxy. If we tried to count halos instead of galaxies, the number inside the observable universe would be much larger. The luminous galaxy census is a partial inventory of a deeper, darker pattern. Dark matter also shapes the cosmic web itself. The filaments and nodes we saw earlier are essentially dark matter structures with ordinary matter falling in and forming galaxies along them. In a sense, galaxies are just the brightest parts of dark matter filaments. When we produce maps of galaxy positions and infer the underlying density field, we are using luminous tracers to reconstruct the distribution of dark matter. The web we see in galaxy redshift surveys is a sketch of a more massive, invisible web. The ratio between ordinary matter and dark matter matters here as well. Observations suggest that only a small fraction of ordinary matter actually ends up in stars inside galaxies. Another fraction remains as gas in galaxies and clusters. A significant portion floats between galaxies in the intergalactic medium. Most of the gravitating mass, however, is in dark matter. So when we say there are 2 trillion galaxies, we should remember that the total mass budget is dominated by something we do not yet understand. This ignorance is frustrating and exciting at the same time. On one hand, our galaxy counts and models of structure formation rely on a component of the universe whose true nature is unknown. We do not know whether dark matter is made of particles we could detect in a laboratory, or whether it reflects some modification of gravity on large scales, or something stranger. On the other hand, the fact that galaxy statistics, lensing measurements, rotation curves, and the microwave background all tell a consistent story gives us confidence that whatever dark matter is, it behaves in a well-defined way in the cosmos. For the purposes of counting galaxies, dark matter sets the rules of the game. It decides where potential wells form, how deep they are, how quickly they merge, and which halos are likely to be able to form stars. The luminous census we quote is an emergent property of that dark framework. Change the properties of dark matter in a simulation, and you change the number and distribution of galaxies that appear. In this sense, 2 trillion is not only a statement about how many galaxies we see, it is also a constraint on the invisible physics beneath them. In the next part, we will push our view of time even further. We will look back to the era when the first stars and galaxies ignited, and outward into the vast spaces between galaxies, where most ordinary matter actually lives. You will see how early galaxies, bright quasars, and the thin intergalactic medium together complete the picture, and why counting galaxies alone still misses much of what the universe is made of and how it has changed. Look at a Hubble or James Webb Deep Field, and you are not just seeing distance, you are seeing time stacked in a single frame. The faintest, reddest smudges in those images are galaxies from an era when the universe was still a child. Between those smudges lies a thin fog of matter so diffuse that it looks like nothing at all, yet it contains most of the ordinary atoms in the cosmos. To understand what our galaxy count really means, we have to visit those first galaxies and the vast medium between them. Only then can we see how incomplete any count of bright islands alone really is. We start very early, long before the first galaxies. After the Big Bang, the universe was hot, dense, and smooth. As it expanded, it cooled, and the cosmic microwave background formed. For a while after that, there were no stars, no galaxies, just a dark cosmos filled with hydrogen and helium gas and growing ripples of dark matter. This era is sometimes called the Cosmic Dark Ages. The raw ingredients for galaxies were in place, but no objects had yet formed to light them up. As dark matter clumps grew, gas began to fall into their gravitational wells. In the first small halos, that gas could cool, fragment, and ignite the first generation of stars. These so-called population 3 stars were likely very massive and short-lived. They burned hot, poured out intense ultraviolet radiation, and died in powerful supernova explosions. In doing so, they seeded their surroundings with heavier elements and helped clear out bubbles in the surrounding gas. Their brief lives were the opening act for galaxy formation. From many such seeds, the first galaxies assembled. In the deepest images, and in simulations, we see them as small, irregular systems, often only a fraction of the size of later spirals. They were messy, full of clumps and bursts of star formation, and prone to frequent mergers. When we look at a very distant red dot in a James Webb image, we are often seeing one of these early systems as it was when the universe was less than 1 billion years old. Its light has been stretched into the infrared by cosmic expansion and dimmed by distance, yet it still reaches us as a faint whisper from that young era. One of the surprises from the first James Webb data was how bright and numerous some of these early galaxy candidates appeared to be. If the initial estimates hold up, they suggest that the universe formed substantial structures faster than many models predicted. That could mean that star formation in small halos was more efficient than we thought, or that our understanding of feedback from the first supernovae needs adjustment. It might also mean that some early candidates are being magnified by gravitational lensing, tricking us into overestimating their brightness. Either way, the details of the early galaxy population are still being hammered out. While these first galaxies were turning on, they were also transforming the space between them. The universe at that time was filled with neutral hydrogen, which absorbs ultraviolet light strongly. As stars and young galaxies pumped out high-energy photons, they began to ionize this hydrogen, tearing electrons away from protons and carving out bubbles of ionized gas around themselves. Over hundreds of millions of years, these bubbles grew and overlapped in a process called reionization, gradually turning the intergalactic medium from neutral to ionized. We study this transition not by seeing the gas directly, but by using bright background beacons as flashlights. Quasars, which are supermassive black holes actively accreting matter in the centers of galaxies, shine so intensely that their light can travel across much of the observable universe. As that light passes through intervening clouds of hydrogen, specific wavelengths get absorbed, creating a forest of narrow lines in the quasar spectrum. This pattern, called the Lyman alpha forest, is a sensitive probe of the density and state of hydrogen in the intergalactic medium along that line of sight. By examining many quasars at different redshifts, astronomers have pieced together a history of the intergalactic medium. They see that at very high redshifts, close to the time of reionization, neutral hydrogen absorbs strongly, indicating that much of the gas between galaxies was still opaque to ultraviolet light. At later times, the absorption pattern changes, showing that most hydrogen has become ionized and that the medium has become transparent in those wavelengths. The galaxies we count are the sources that drove this transformation, but the majority of ordinary matter involved lives in the medium itself, not in the galaxies. This realization leads to another puzzle, often called the missing baryons problem. When we measure the total amount of ordinary matter in the universe from the cosmic microwave background and from element abundances, we find a certain expected density. When we add up all the matter in stars and cold gas inside galaxies, and in hot gas inside clusters, we come up short. For a long time, about half of the expected ordinary matter was unaccounted for. It was not in the galaxies we could see, and not obviously in the clusters either. The solution has been to look between galaxies and between clusters in new ways. X-ray and ultraviolet observations have revealed a web of warm and hot gas threading the space between galaxies, especially along filaments. This diffuse material, known as the warm-hot intergalactic medium, is thin enough that it does not glow brightly on its own, but it can be detected through faint emission and through absorption lines in the spectra of background quasars and galaxies. When this component is included, the missing baryons largely reappear. Most of the ordinary matter in the universe is in this sparse intergalactic gas. This means that when we count galaxies, we are not counting where most of the atoms are. We are counting where most of the starlight is. Galaxies are dense nodes where gas has cooled and collapsed far enough to ignite stars. The intergalactic medium is the vast reservoir that feeds them and receives their outputs. Winds from supernovae and active galactic nuclei blow metals out of galaxies into this medium, enriching it over time. Gas flows along filaments from the medium into halos, replenishing galaxies and sustaining star formation. The two components are in constant exchange. Thinking in time, galaxies and the intergalactic medium form a coupled system. Early on, small galaxies lit up and began to carve ionized bubbles in the neutral gas. As more galaxies formed and merged, reionization completed, and the universe became transparent to ultraviolet light. Over billions of years, some gas cooled into galaxies, some was heated and expelled back into the medium, and some remained in the filaments and voids, never quite collapsing. The galaxy count we see at any moment is a snapshot of how much gas has managed to cross the threshold from diffuse medium to dense star-forming systems. From this broader view, our famous 2 trillion galaxies are only part of the cosmic ledger. They are a visible subset of structures sitting on dark matter scaffolds and exchanging matter with an even larger intergalactic reservoir. Missing faint galaxies is one source of uncertainty in the count. Missing the diffuse gas between galaxies is another source of misunderstanding about where the universe actually stores its matter. When we correct both, we find that light traces only a fraction of the total story. There is a quiet beauty in this. Every deep image of galaxies is also, secretly, an image of their environment. The space between smudges is not nothing. It is the medium through which light travels, the reservoir that birthing and dying stars tap into, the fog that was once neutral and is now ionized. When you look at a field of galaxies at different redshifts, you are reading a layered story. At each distance, galaxies and the intergalactic medium are at a different stage in their shared evolution. In the final part of this journey, we will step even further back. We will ask what all of these numbers and structures mean for us as humans. We will tie the changing galaxy counts, the dark scaffolding, and the thin intergalactic gas back to our own existence and to the way we think about our place in the cosmos. The science does not become less precise in that step, but its purpose becomes more personal. After all, counting galaxies is really a way of asking how a universe like this could ever have produced someone like you, sitting here listening to its story. Everything we have talked about so far lives in a narrow slice of cosmic time, a universe 13.8 billion years old, galaxies still busy forming stars, deep fields full of structure. It feels vast to us, yet in the life story of the cosmos, we are early. To see what our galaxy census really means, we have to jump forward in imagination. We need to visit a future where the universe has aged, stretched, and thinned so much that our 2 trillion galaxies are only a memory. The key actor in that future is something we barely understand today: dark energy. In the late 1990s, astronomers discovered that distant supernovae were dimmer than expected. That meant the expansion of the universe was speeding up, rather than slowing down. Some unknown component of the cosmos was acting like a kind of negative gravity on large scales, pushing galaxies apart faster and faster. We call that effect dark energy. It is a label, not an explanation. As dark energy dominates, the Hubble expansion accelerates. Galaxies that are not bound to us gravitationally are carried away more and more quickly by the stretching of space. Right now, we can still see many of them, because light they emitted long ago is still arriving. In the far future, that supply will run out. There will be a time when any new light they send will never reach us, because the space between us will be expanding faster than the light can cross. Our local group is held together by its own gravity. The Milky Way, Andromeda, Triangulum, and their dwarfs form a bound island. Over the next few billion years, these galaxies will merge into a single, massive system. It will likely be a dim giant, its star formation slowing as gas is used up or heated. The rest of the universe will continue to expand away. Eventually, all galaxies outside this local island will slip beyond our cosmic event horizon. No signal launched from them then will ever arrive here. To an astronomer living in that distant epoch, the sky will look very different. There will be one huge galaxy in place of many. The cosmic microwave background will have stretched to such long wavelengths that it becomes undetectable. The Hubble expansion will be impossible to infer because there will be no visible external galaxies to track. From that vantage point, it would be natural to conclude that the universe is static and finite. The evidence we currently use to infer dark energy in cosmic history will simply not be available. Long before that point, star formation will already be in decline. Galaxies today are steadily turning gas into stars. The most massive blue stars burn out quickly in a few million years. Smaller stars, like the Sun, last billions of years. The smallest red dwarfs can burn for trillions of years. Over time, gas reservoirs shrink. Feedback from supernovae and black holes heats and expels gas. The cosmic star formation rate, which has already dropped from its peak billions of years ago, will continue to fall. In the very far future, most new star birth will have stopped. The universe will be filled mainly with long-lived red dwarf stars, cooling white dwarfs, neutron stars, and black holes. Bright blue stars will be memories. The galaxies that remain, including our merged local island, will grow redder and dimmer as their remaining stars age. The night sky on a habitable planet, if such worlds still exist, will be darker and more sparsely decorated than ours. On even longer timescales, exotic processes come to dominate. White dwarfs will cool and fade into black dwarfs, stellar corpses barely above absolute zero. Orbits may be disturbed by encounters and by slow gravitational interactions, flinging some stars into intergalactic space. Black holes will continue to merge and grow, swallowing matter and compact objects. According to our current understanding of quantum physics, even black holes are not eternal. Over extreme times, they slowly leak energy through what is called Hawking radiation and eventually evaporate. The timescales involved are so huge that ordinary language almost breaks. Trillions of years for red dwarfs, vastly longer for black hole evaporation. By that era, any practical census of galaxies will be meaningless. Structures that once counted as separate galaxies will have merged or dissolved. The accelerating expansion will have cut off any possibility of new information arriving from beyond the local island. The universe will be a scattering of isolated, nearly empty regions, slowly cooling and fading. Now turn back from this distant future to our current efforts to count galaxies and understand the cosmos. You and I live at a special time. Not special in the sense of being chosen, but special in terms of available evidence. The sky still shows us galaxies at many distances. The cosmic microwave background is still measurable. The expansion of the universe can still be tracked. We can still see the cosmic web and watch galaxies at different stages of their lives. We have access to a wide range of clues that future observers in the same universe will never recover. Even with that advantage, there are hard limits to what we can know. One is the cosmic horizon. Regions of space whose light can never reach us are permanently beyond direct observation. They may contain countless galaxies, but they will never appear in any catalogue we compile. Another is the opaque early universe. Before the cosmic microwave background formed, the cosmos was dense and ionized. Photons could not travel freely. We can model that era and check our models against later evidence, yet we will never see it directly the way we see galaxies. Black holes mark another boundary. The event horizon of a black hole separates what can, in principle, send signals to the outside from what cannot. We can study matter falling in, we can detect the waves from black hole mergers, we can model their interiors with equations. We cannot receive light or information from inside the horizon. Any structures, stars, or perhaps even hypothetical civilizations that cross that boundary are gone from our observable universe forever. There are also limits set by our own tools and by noise. No matter how good our telescopes become, there will always be a faintest galaxy that falls below detection, a furthest distance we can probe, a most subtle signal we cannot separate from background fluctuations. We can push those limits back with better technology and clever methods. We cannot remove them entirely. In that sense, every number we quote, including the 2 trillion galaxy estimate, is framed by permanent uncertainty. These limits are not a failure of science. They are part of the structure of reality as we understand it. General relativity and quantum mechanics, our best theories of space-time and matter, imply horizons and irretrievable information. The cosmic expansion creates regions that can never influence one another again. The early hot plasma erases detailed information about the very first instance of the universe. Scientific progress can tighten our models and refine our estimates, but it cannot break those fundamental walls. So what does a galaxy count mean in such a universe? It is not a final answer that reveals the whole truth. It is a carefully posed question and a provisional reply, valid within a certain time, scale, and set of assumptions. It tells us how many luminous structures of a particular kind exist within the part of the cosmos we can see, given what we know about dark matter, gas, and cosmic history. It carries an implicit acknowledgement that there is more out there than we can ever measure. Rather than making the universe feel smaller, that acknowledgement can make it feel richer. There is the part we can map and count, full of galaxies and structure and history. There is also the part that lies beyond any possible observation, whose details we will never know. Between them sits a boundary that is not about human weakness, but about how space-time works. Our job is to understand as much as we can on our side of that boundary, and to be honest about where it lies. In the final part of this journey, we will bring the story back to us. We will trace how the idea of countless galaxies reshaped human thought, how our growing census changed philosophy as much as physics, and how knowing that we live in a universe of unseen limits and uncounted worlds can shift the way we feel about our brief lives under one ordinary star in one ordinary galaxy among the many. Stand under a dark sky and count what you can see. A few thousand stars, a pale river of the Milky Way, maybe a faint blur of Andromeda. Now place beside that the idea of 2 trillion galaxies inside our observable universe. The contrast is absurd. Your eyes report a quiet backyard. Your instruments and equations whisper that you live in an endless city. That gap between what experience tells you and what the universe actually is may be the most important part of this entire story. Humans did not always live in a universe of galaxies. For most of history, the night sky was a dome above a flat world or a small sphere around a central Earth. The Milky Way was a mysterious band, perhaps the road of the gods or spilled milk or an old scar in the sky. Even when telescopes revealed that the Milky Way was a structure made of stars, many astronomers still thought of it as the whole universe. The faint smudges on early photographic plates were just that, little clouds in our own backyard. In the 18th century, thinkers like Immanuel Kant speculated that some of those faint nebulae might be island universes, systems of stars far beyond the Milky Way. It was a bold idea, ahead of the evidence. More than a century later, in the early 1900s, the argument over the nature of the nebulae came to a head in what is now called the Great Debate. Harlow Shapley argued that the Milky Way was huge and that the nebulae were part of it. Heber Curtis argued that some nebulae were their own distant galaxies. There was no clear winner that night. The data were not yet strong enough. The turning point came when Edwin Hubble used variable stars called Cepheids to measure distances to some of those nebulae. The numbers were too large to fit inside the Milky Way. These objects had to be separate galaxies, far outside our own. In one stroke, the known universe expanded from a single star system to a cosmos filled with island universes. The galaxy count was still small by modern standards, only a few dozen well-measured systems, but the philosophical shock was immense. We were no longer at the centre of a single grand structure. We were citizens of one galaxy among many. As telescopes improved and surveys expanded, the number of known galaxies climbed into the thousands, then the millions, sky maps filled with dots. Yet for everyday thought, it was still easy to shrug and file the idea away as background trivia. Yes, there are galaxies out there. Yes, the universe is big. Then the deep fields arrived, and later, simulations and reanalyses, and the number leapt again, this time into the realm of hundreds of billions, and then to the now famous order of 2 trillion. Each jump was not just a technical update, it was another nudge to our sense of scale. There is a pattern in all of this. Every time we get better at counting, our place shrinks and the cosmos grows. The Earth turns into a planet among planets. The Sun becomes an ordinary star in a galaxy. The Milky Way becomes one galaxy among many. The visible galaxies become a subset of a much larger web. Even the observable universe itself becomes a finite bubble inside something potentially larger. The count of galaxies is one thread in a long story of decentering ourselves. Yet this story is not simply about making humans feel small. If it were, it would be easy to tune out. The other side of the story is about connection. The atoms in your body were forged in stars and in the explosions of massive suns. Those stars lived in galaxies whose histories are stitched into the cosmic web. When you trace the chain of events that led to you sitting here, listening to a story about galaxies, it runs through dark matter halos and merging dwarfs and star-forming disks. The census of galaxies is not just a list of distant objects, it is a record of the factories that built the ingredients of your own blood and bones. There is also something deeply human about the way we build that census. We take small, imperfect samples and extrapolate. We design machines to extend our senses, and then design theories to interpret what those machines show us. We accept that some regions of the universe are forever hidden and work within those limits honestly. 2 trillion is not a boast. It is a carefully negotiated truce between what the data allow and what our models demand. In learning how to count galaxies, we learn how to confront ignorance without pretending it is not there. Knowing that the number is provisional can change how you feel about science itself. It is tempting to treat big cosmic figures as final answers carved into stone. In reality, they are checkpoints on a moving road. They tell you not only what we know, but also how we know it and where the uncertainties lie. The fact that the galaxy count may change as new telescopes come online is not a sign of weakness. It is a sign that we are still listening. On a more personal level, living in a universe of trillions of galaxies can sharpen both humility and meaning. Humility, because it undermines any easy story about being the central purpose of creation. The cosmos clearly did not arrange itself for our convenience. Its structures and timescales are far larger than anything our ancestors imagined. Meaning, because against that background, your existence becomes an improbable, fragile flame. Out of all the ways matter could arrange itself, you are a configuration that can understand at least a little of the pattern you live inside. There is a quiet comfort in that. You are not the centre, but you are not nothing. You are a local embodiment of the same laws that shape galaxy clusters and black holes and intergalactic gas. The neurons in your brain fire with electrical signals governed by the same physics that dictates how stars shine. When you feel curiosity about the universe, that curiosity is one of the universe's ways of looking at itself. The galaxy count is part of the mirror it holds up. If future beings, human or otherwise, look back at our era, they may remember us not for the exact number we quoted, but for the fact that we tried to measure it honestly. For the fact that we noticed how the night sky misleads the eye and built tools to see beyond it. For the fact that we could feel both awe and responsibility in a universe that will go on without us. 2 trillion galaxies are a background against which human choices still matter, especially to each other. So the next time you see a deep field image, packed with tiny smudges, you will know more of what you are looking at. Each smudge is a galaxy with its own history, its own stars, and perhaps its own planets and questions. Many more galaxies hide beyond the frame, too faint or too distant for that image to catch. Beyond those lies an unobservable realm we can never count at all. Somewhere in that structure, on one planet, around one star, in one galaxy, you got the chance to exist and to ask how many galaxies there are. That question does not have a perfect final answer. It probably never will. But in asking it, and chasing the best possible reply, we carve out a small zone of understanding in a vast, indifferent universe. We turn the night sky from a flat ceiling into a story, and we discover that in a cosmos of unthinkable scale, meaning is not handed down from outside. It is something we generate together under the glow of one ordinary star in one spiral arm of one galaxy among the many.